In this video, we want to derive the wave function for the free particle. And the free particle corresponds to this solution for the Schrödinger equation simply when there is no potential. So when v of x is equal to 0, we have this equation. And this is much easier to solve than most equations that you're faced with, especially in quantum mechanics, but the difficulty lies in the fact that there are no boundary conditions, so there's a lot of ambiguity around what this can actually be, or what this should be. So, like, just say we have some matter particle, and it has some energy. We know that this corresponds to h bar omega, where omega is the frequency of this wave, and this is from de Broglie's formula. And then we also have that the momentum of this particle is h bar times k, where k is equal to the square root of 2 times the mass times the energy over h bar. And we'll find that the solution to this equation here can be in one of 3 different forms. So we know it's going to be a traveling wave, a traveling plane wave, and let's say it's moving in the positive x direction. Then we could have cosine kx minus, and if it's traveling with this frequency omega, we put omega here, and then t for the time dependence. So this is one solution that we could work with. Or we could have sine and the third possibility is that instead of this cosine and sine, we have a phase factor. And then this has another sort of representation, given that we have a complex number here. We can also have it in this form. And these are all the different ways that you could have a matter particle traveling in the positive x direction, based simply just off the solution to this equation and then adding the time dependence. And now we want to just try a few of them out and see what happens if they could actually serve as real representations of what this free particle should look like. So we'll start with our cosine solution. And let's say we have a particle that's equally likely to be traveling to the right in the positive x direction or to the left in the minus x direction. So we can just assume that this wave function is an equally weighted superposition of cosine kx minus omega t and cosine kx plus omega t. And we can expand this to give us cosine kx times cosine omega t. And immediately this is unacceptable. It's not going to work for us. And the reason for that is, if we look here, we see that there are moments in time, specifically when t is equal to pi over 2 omega, or 3 pi over 2 omega, or 5 pi over 2 omega, and so on, that this term here is just going to evaluate to 0, and we have a particle that at certain moments of time has completely ceased to exist in all of space. And that is a problem. So immediately we can say, no, this is no good. Our solution for this free particle, we know at the very least, is not going to be cosine. And we can see that the same thing is going to happen with sine. If we have a particle, again, equally likely to be moving in the right, or in the positive x direction and the minus x direction. We get a similar formula, again with this unacceptable time dependence here, which evaluates to 0 at certain moments in time. So no good. And finally, we're left with our phase factor solution. And I'm going to choose to, for the first term where we're moving to the right, I'm going to have kx minus omega t. And then in our second term, I'm going to swap the sign. But this wave function is going to be representing moving to the left. So it's plus omega t here. And now if we rewrite this, we have the following here. And we can see that we can factor out this time dependence. So let's go ahead and do that. And we're left with e to the I kx plus e to the minus I kx. And this is just equal to 2 times this phase factor times cosine kx. And finally, we've come across a solution that's somewhat acceptable because, or not somewhat, this is a good solution for now, because this time dependence term never evaluates to 0. It always has magnitude 1. So that's good. I mean, we have that at certain areas in space, we won't measure the particle throughout time, but we don't have the reverse, that in certain moments of time we won't find the particle anywhere at all in space, which is not allowed, of course. Just by simple ideas of probability, we should be able to measure the particle at some point. And just like that, we've obtained a solution, a temporary solution to this free particle traveling in the positive x direction. And in the next video, we're going to examine some consequences of this and see if we can try and normalize this solution.